Hello folks, welcome back to the video tape review and solution. So this video will focus on the first part of the regression. So first of all, if you are not clear about the regression, you can come back to the class note 21st and 22nd and 23rd, which contains some codes and formulas, derivations of theories over there. So now we will have a very quick review of the regression for the exam. First of all, the first concept is the least square line. In our class, we define the least square line as the y head equals to the beta 0 head plus beta 1 head x. So how could we find out the beta 0 head and beta 1 head? Most of the time we have codes in R or in JMP so that we can look at the output in the parameter estimations for both R and JMP to find out the beta 0 head and beta 1 head to fit the line. So the second thing is about R squared. We have capital R squared and we have small r squared. So the capital R squared is called the coefficient of determination. So to interpret the R squared, we have if the R squared equals to 0.75, we claim that, to be safe, we add approximately here. We claim that approximately 75% of the observed variation in the model can be explained by the simple linear regression relationship between the independent variable and the dependent variable. So the independent variable is x, and obviously the dependent variable is y. For the correlation, we have the correlation r, squaring the r equals to the r squared. So that we should say, oh, the r is the square root of r squared. But if you think of this, you may be missing something. So we need to be careful here. We have to look at a scatter plot. If the slope is appeared to be positive, we say that we have positive linear relationship. Then we take the positive square root for the r squared for the correlation. Whereas if the slope is appeared to be negative, then we take negative square root of the r squared. So remember, both the r squared, that is the coefficient of determination, and the correlation r only work for evaluating linear relationships. So if the plots have demonstrated that the model is not a linear relationship, for example, they appear to be inverted U-shape, monotone increasing or decreasing, then using the r squared or the correlation coefficient r may not be valid to evaluate such relationship. We also talk about the normal assumption for the linear model. The simple linear model is yi equals to beta 0 plus the beta 1 xi plus epsilon I, where the yi is the response or the dependent variable for the observation I, for I equals to 1, 2 to n. Xi is the observed value for the predictor for the observation I, whereas the epsilon I denotes the error term for the observation I. Or we can use the matrix form, which is the capital Y equals to beta 0 plus beta 1 times capital X plus the epsilon. We have 4 normal assumptions for linear model. First of all, we need all the observations are independent of each other. Secondly, we need an errors term epsilon 1, epsilon n up to epsilon n are random and independent as defined inside the class. Particularly, we need the magnitude of any error term does not influence the value of the other error terms. So again, if the error terms appear to be monotone increasing or decreasing, U-shape or inverted U-shape as appeared into residual plots, then our normal assumption for the linear model is validated. Okay, if you are not familiar with the second assumption, pause your video to come back and check your notes. And the class note 22 and 23, I have included something over there. So let's just move on. We also need the error terms to be normally distributed with the mean 0 and with the same variance that we called homoscedasticity. Notationally speaking, we actually need the error terms epsilon I, which is independent and identically distributed, which is the IID in the short term, normal distribution with mean 0, and the constant variance sigma square. For all the observations, for all the error terms, epsilon 1, epsilon 2 to epsilon n. So now, if the normal assumptions are fulfilled, then we can further have the response variable yi follows a normal distribution. Notationally speaking, we have the yi are independent and identically distributed with normal distribution with mean beta 0 plus beta 1 xi and with the variance sigma square for all the observations. Is it clear? If not, pause your video to come back to go over normal assumption again before the exam. Now we move on to look at several terms that we use frequently inside our regression framework. First of all, we talk with the slope, which is the beta 1 head in our regression line. As you remember, the y hat equals to the beta 0 hat plus beta 1 hat times x. So the beta 1 hat could be found in the output for either R or jump. But if you are unfortunate enough, I hope you to also know about the formula about the beta 1 hat, which is a summation of I equals to 1 to n, yi minus y bar times x1 minus x bar over the corrected sum of square, which is the summation of I equals to 1 to n xi minus x bar to the square. This is our formula for the slope. So after finding the slope, we have our formula for the intercept. Beta 0 hat equals to the mean response of y, which is the y bar, minus beta 1 hat times the mean of x bar. For the standard errors for slope and intercept, we have the standard error for the slope beta 1 hat equals to the sigma over the square root of the corrected SS, which is the summation of I equals to 1 to n xi1 minus x bar square. So make sure you know that the sigma here representing the RMSE, and for the standard error for intercept, we have SE to the beta 0 hat equals to the sigma times the square root of 1 over n plus the x bar square over the corrected SS, which is sum of I equals to 1 to n xi minus x bar square. So just come back to the estimate of variance appear in the standard error of slope and standard error for intercept, which is the sigma hat square. Well, actually the same with the sigma defined above. It actually equals to the MSE for the sigma square which is the RMSE square. The formula of this is the summation of I equals to 1 to n yi minus yi hat, which is the predicted value yi hat and the observed value yi, taking their difference and square them over n minus 2, which is our degree of freedom. So any questions before going on? For more information about this part of the derivation, we can look at page 537 in your book. Talk about how to derive the least square coefficient for beta 0 hat and beta 1 hat. I won't go over here, but if you are interested, you can follow step inside the book. Thank you so much.